So here we go. Here are our three cakes. The top one is the temperature cake. Let's have a look at the temperature cake first. Okay, so what you can see is a warm layer on top. Okay, and this is just the permanent thermocline. Okay, you have a warm water temperature controlled stratification in equatorial, tropical, subtropical regions, and that's why you have the warmest water on top, 20 degrees, okay, on top here, and then it gets cold at depth. Okay, and you can see the coldest water can be traced back coming from Antarctic regions, okay, from polar regions around Antarctica. That's all you can see there in terms of the temperature field. Okay, so the salinity field, it's the second panel, gives you another piece of information. Okay, because in this distribution, we can actually, if we look south of the equator, where's the equator actually, by the way? Did you spot it? Equator is something around, look where the mouse is, it's around here. This is the equator. So you actually, in this temperature field, only see a fully developed subtropical gyre in the southern hemisphere. Okay, so we focus at the southern hemisphere, and what we can see in the salinity field is actually Antarctic intermediate water. It's a signature, it's a lower salinity water. Okay? It's a tongue of lower salinity water pumped into the ocean interior. It's actually Ekman pumping that produces this feature. Okay, and it moves into the interior and ends up at depth of about 1.5 kilometers. You might say, oh, there's something similar in the northern Indian Ocean, but it's not. This feature is missing. All you get in the northern, there is a tongue of higher salinity water. You see that? See, look at the colors, look at the figures. And look at the numbers here. This is a tongue. It's not intermediate water. It doesn't come from subpolar regions. Okay, it has totally different characteristics. And how different it is, before I tell you a little bit about the other details, how different it is can be seen in the dissolved oxygen distribution. Okay, the lowest panel is the vertical transect dissolved oxygen. Okay, starting on the left, this one is the northern margin of the Indian Ocean. Okay, and on the right is the Antarctic region. You can see that the southern Indian Ocean is everywhere well ventilated in terms of oxygen, and you get critically low level as you go towards the northern Indian Ocean. And here you can see very, very low values. Below 2 milliliters per liter is the critically low levels. Okay, and you can see it from almost the surface down to depth of 2 kilometers in this region. And the main reason why it exists in this region is you don't have bottom water formation. The deep water doesn't, the North Atlantic deep water doesn't spread into that much into the North Indian Ocean, and you do not have the formation of intermediate water in this region. Okay, and this is a natural feature that you have this oxygen minimum zone, the dead zone in this area. Okay, so quite some details here. It's not that, I mean, it's relevant to the marine ecology, okay, because you have only certain extreme type of species can survive in no oxygen in conditions. So this one really sets conditions for the marine species, which are largely constrained to live very close to the surface in this area anyway. Okay, so what else is mentioned here? Maybe we come back to that later on. It's something called central water. Okay, central water is the water within the permanent thermocline near the surface. Indian central water, and we actually have different type of central water in this area. Okay, where we have different type of contribution. We look at that on the next slide. So what happens within the upper, say 1,000 meters of the water column has different contributions. This is a little detail, but maybe it's interesting to know that. Okay, so let's continue.